Okay, so originally I had planned to dedicate this lecture to introducing other algorithms of nonlinear dimensionality reduction, but then I thought that it was maybe better to actually show you a bit of results the algorithms we already studied give. Also because for the other algorithms we need a bit more of machinery on the theoretical side. At least to understand why they work, to explain them, not really, but anyway. So we will be comparing the three nonlinear dimensionality reduction methods we studied, which are the IsoMap, the locally linear embedding, and the linear tangent space alignment. Yes. Now, to briefly recall you, the IsoMap algorithm started by determining the distances between any 2 points on the manifold of our data. So we produced a graph using small distances connected near points, and then traveling through the graph with a, with a sensible algorithm, not the naive one, to determine the distances between any 2 points on the manifold. And then we built a projection on some Rn, with n possibly small, that preserved as much as possible these distances. All these methods, in the end, boil down to, the last step in almost every dimensionality reduction method is some eigenvector problem. So at the core of every of them, there is some eigenvector solver which finds the eigenvectors of a possibly very big matrix, which is usually sparse. So anyway, there are technicalities which do not have anything to do with the Riemannian geometry part, but with like the numerical part. So a course about nonlinear dimensionality reduction wouldn't be complete without the Swiss roll, which is the standard data set for this kind of algorithm. We will use two kinds of data set. Classical, the original version, let's say. So we have a surface in R3, and we pick, we sample points from it in a uniform way, or at least uniform in the parameterization. And then we add some noise, some normally distributed noise with mean zero and some variance. Here in the picture, I'm going to show you the variance is, the standard deviation is 0.5. So it's sigma, not sigma square. This is the Swiss roll. So you probably, can imagine it is just a piece of the plate, a rectangle rolled up. Girella, fondamentalmente. The names come from a suite, so the Swiss roll was a suite. And the colors are just to tell the points one from the other. By the way, if you apply, I didn't do it, but it's also interesting to apply something like PCA to this kind of data set, and PCA won't recognize the two-dimensionality. It will tell you that there are three almost comparable eigenvalues, so you have to take take an embedding with three components, which is the actual embedding we have here. It won't unroll the Swiss roll, which is the thing you would like any reasonable manifold learning method to do, so to recognize this is a two-dimensional thing rolled up in R3. If you add some noise, what you obtain is a fuzzy version of it, so the points are not exactly lying on the surface, but they are more or less there. Okay. So as I told you, because I just thought of that, I didn't apply the PCA to the data set, so I don't have a picture to show you how a PCA embedding with the first two eigenvectors would look like, but you can do it on your own, I think. I mean, PCA, it's quite easy. Now, let's just compare the algorithms on, we will compare just the pictorial result. I won't be giving you like exact times of execution or errors or things like that. You can recover that. Probably I will, like I did for the, I put on the course website a PDF, which is the printout of a Jupyter notebook for the graph embedding problem through the Laplacian matrix of the graph. And I think I will do the same for this comparison, so you can actually play with them if you want, and add like and check the error or the execution times and stuff like that. Now, our data set is composed by 2,000 points in R3, and we apply these three algorithms, all with the KNN algorithm to build the graph, so the K nearest neighbors, with K equal 12 here. Now, why 12? Well, we will talk about it later. Obviously, you cannot choose any value for that. We use this because we would like, the KNN guarantees that, if you choose K wisely, so we will be talking about that now. If you choose K wisely, the KNN algorithm will guarantee that there will be no holes in your dataset graph, which are not, which shouldn't be there. So there will be no holes due to poor sampling, at least at some scale, or to the opposite, too much connectivity. If you pick K too high, weird things can happen to the geometry of the graph. Also that you can try also that. Anyway, execution times are definitely in favor of LLA, then LLE, then LTSA, then IsoMap. And more or less, they are like, LTSA is twice as slow, and IsoMap is 5 times as slow than LLE, the local linear embedding. Now, local linear embedding, okay, I told you again about IsoMap. Local linear embedding works by writing every point on your manifold as a linear combination of nearby points with respect to the graph. Obviously, this is not exact, but you do the best you could, and then you try to find lower dimensional points which respect the same kind of linear combinations at every point, again with some error. And LTSA writes everything like its tangent plane, and then tries to glue up all the tangent planes in something straight. So it actually tries to find the parameterization of your surface. Now, this is what the plot of two components of the three algorithms looks like. So IsoMap, LLE, and LTSA. You see that LTSA and IsoMap give more or less the same result. LLE gives this weird shape. But more or less, if you just look at the very rough level, all three of them managed to unroll the Swiss roll because the colors are in the right spectrum. So they all were able to unroll the Swiss roll. Now, the red part being left or right is just a sign thing, so we don't care about that. Also, if you look at the gradient of the color, which more or less tells you where you are on the Swiss roll, IsoMap and LTSA give almost the same gradient, because obviously this unrolling might alter the metric, the angles and stuff like that. But here it seems that between them it didn't change much. Well, LLE changed a lot because obviously you start big on the red part and you go small on the blue part, so it means something squeezed down. Okay, now let's try and vary k and see what happens. We start from 4 and up to 19 using noiseless data. So the only parameter here is the k we are using for the k neighborhood, k nearest neighbors part of the algorithm. Which actually in our algorithm, this is a sort of, usually people think about it as a sort of pre-processing of the data, but it's not true, because the way you build a graph has something to do with the way you think your data are sampled on the manifold. And so there are connections between the effects of these parameter choice and the geometry of the manifold. So it's not something which doesn't have anything to do with the geometry part. Now this is with k equal 4, the three algorithm. You can see that they're not really performing very, there are holes here. And these holes here are actually the result of a poor connectivity of a graph. It's connected obviously, but it has a lot of cycles and stuff that shouldn't be there. There are not actual holes in the data set, which you looked at it before. It's like a whole strip, uniformly sampled, but obviously if you sample uniformly on a rectangle and then you roll it, the internal part of the roll will have more points than the external part of the roll, but on the rectangle they will be the same. So there's a stretch somehow which alters the local distances between points. At least IsoMap kind of has the gradient we would like to see from red to blue. LLE is disastrous. It gives you all the internal part of the roll and it squeezes the two endpoints here. And LTSA is even worse. I don't know. Okay, if you go up with k equal 5, IsoMap starts to look like something you would like. LLE at least gets right the last part, so it tells you, it seems to tell you that it's a linear space, a straight line and not a two-dimensional thing, but more or less, at least the last part of the gradient of the colors is right. LTSA disappeared, probably everything is here, so you cannot even tell the points apart. With k equals 6, well, IsoMap is good, okay. LLE now clearly sees a straight line with almost the right gradient, and LTSA also, because this is exactly the gradient we would like to have, only it's a vertical line and not a strip. Now, with k equals 7, things get really better. IsoMap and LTSA just got the more or less the right picture, even if IsoMap still has some holes. You could, if you want to do something like topological data analysis, this could be a pre-processing step, and sometimes it is. So you lower dimensionality, so you get maybe from your 2,000 dimensions data set of images, you get out a three-dimensional thing, and then you look for holes and, persistent homology of these three-dimensional representation and not of the original submanifold of 2,000 dimensions. So also the fact that let me call them holes because we are in the plane, so the homology is just the holes. The holes in our two-dimensional representation should correspond to holes in the actual dataset, and this is not true in this case because the dataset is, nice and, well, I wouldn't say continuous, but uniformly covered. So these parts here are just glitches due to a small k, or at least non-sufficient k. LTSA is nice. LLE is kind of getting out of the one-dimensional representation, but not really. At least the gradient is right. Now, for k equal 8, we get the picture we saw before. Now, obviously, this is squeezed because I had to reduce the dimensions. No, it was 12 before, not 8, so not really. Now 9, 10, 11, 12. This was the one we saw before. Here, I mean, in all the previous ones, LLE wasn't really two-dimensional, but in fact, I mean, it wasn't constantly two-dimensional, but it sort of was. It was a triangle, so it's I mean, a decent two-dimensional shape. And IsoMap and LTSA are behaving very well. Now, K13, 14, I don't think there are surprises anymore. Yeah, I mean, sometimes they flip, but it's, again, a sign problem. And so now it remains constant. This, and this was the last one. This kind of data set doesn't really behave bad when we go up with the values of k. Obviously, if you take too many, like there are 2,000 points, if you take a value of k which is comparable with 2,000, you are connecting almost all the points. So, I mean, it will cause some problems. If you run the algorithm with k equal 500, probably you have some problems, obvious problems, because you're connecting one point to a quarter of the points that you have there. So it's going to screw up the local geometry. Now, noise in the data. So how about what if we have some noise, which is usually the case in our data? So it's not a perfect data set. We now fix k equal 12 and introduce noise in the data, sampling from a normal distribution with sigma varying from 0 to 0.65, just to have a decent number of things, and mean 0. This is not a lot of noise, actually, but it has its effects. So this is with noise 0, the picture we saw before. Noise 0.05, 10. You see here, for example, you see that LTSA is passing from a two-dimensional representation to something which looks like more one-dimensional. Not really, but now, yes, it definitely is one-dimensional. Also, LLE is almost one-dimensional with the right gradient again, but they lost the dimensionality of it. So there are sort of the point is that the algorithm cannot distinguish anymore like, look at this surface. There is a normal variation due to noise, in some sense. There is the roll, and then there is a horizontal variation, which is the width of the strip that you roll up. Now, at this point, the algorithm cannot tell from the noise, which is actually small, and the noise you're adding is on average like 3-4% of the width in the y variable, so it's not that much. But even now, it is very sensitive to that. LLE starts seeing things clearly again. Now, this could look like just an inconvenience, but it's not. It's not like the triangular shape before, because in the triangular shape from before, you had red on one side and blue on the other, and the gradient. Here you have red on the upper part and blue here, and it starts to really deform the geometry of the data. And okay, now this is the end point where you have a boomerang and the stick. IsoMap stays quite stable under the noise. Now, this was all nice, but it was a synthetic data set, so it was built on purpose. it's quite a nice example because obviously you have this thing rolled up, so you should distinguish the points which are close because they are actually close, and those which are close because they are on two nearby sheets of your roll. But again, I mean, it's something in R3, and for example, the execution times on my Windows Surface, which is not a particularly fast machine, were around 2 seconds for IsoMap and 0.4 seconds for LLE, so yeah, really easy. Now, real-life dataset. I've taken from the MNIST training dataset, which is a dataset of handwritten digits. They are all images 28 by 28 in grayscale, or actually black and white mostly, which represent written digits. Okay, so I ran the 3 algorithms first on the dataset built by the digit 2. So I picked out the digit 2, and they are like almost 6,000 images, 28 by 28, so there are 6,000 points in R to the something like 900, a bit less. Now, the digits look, the handwritten digits look like that. So you see there are different behaviors, like a very ornate arc below, a very curved arc above, or everything like straight, or just the arc below, or just the arc above. So you can have different behaviors, and you would like to more or less see this different behavior in your data analysis. So it stands to reason that the set of these, not these 15, but these 6,000 images is not randomly distributed uniformly or even normally distributed in R to the 28 squared. It should be some kind of manifold. Probably it's not really a manifold, but it should project to some kind of manifold, which maybe has really low dimensions. So there are 2 dimensions where it really varies a lot, and then there are other small variations which are very small with respect to the main ones. Now, if we run our algorithms with k equal 15, and LTSA was definitely faster, but there was a, I mean, you can run in a lot of problems with the eigenvector solver, and so you have to change the algorithm sometimes, and this produces weird behavior. But anyway, this is the 2-dimensional representation with IsoMap. And you could see that you have some sort of directions. I mean, I've selected the same 15, I think, and I placed them where they belong on this representation. Now, you could see that, I mean, there are a group where it's less, everything is less curvy and ornate, and there is definitely a region where everything is more twists and curves. And you maybe, I mean, maybe if you like looked a bit more carefully, maybe not with 15 but 40 of these, you could also notice 2 the orthogonal behavior, one regarding the upper part and one regarding the lower parts. But try it. This is LLE. Again, LLE likes this sort of triangular shape. And also here you could say that this part is definitely not as calligraphic as this part. And maybe there is some variation also in this axis, but it's too squished to see. This is LTSA, which is weird. I mean, if I remove the pictures of the digits, maybe you'll understand what happened. Everything ended up here. So the LTSA couldn't tell the the points apart, probably for due to problems with the eigenvector solver, but anyway, that was the algorithm. So now these are all I've not been implementing on from scratch the algorithms. I've been using the algorithms implemented in sklearn, so which is a Python module. So probably on a, I mean, from a like numerical viewpoint, they are soundly written. So anyway, this is the usual picture. You can see that it's clearly a two-dimensional thing. You could also plot the three-dimensional one. I didn't for two reasons. First, it's difficult to tell three dimensions for two dimensions here on a screen. Second, because it's harder to put in a meaningful way the images of the numbers 2. You would like them to rotate when you rotate the view, but it is quite difficult to obtain. But I have also those, and I could, I mean, if I share with you the Jupyter notebook, then you will have interactive 3D plots, and you can rotate them and see what happens, like in the graph embedding notebook. Now, you could also try to apply these algorithms to the whole, or to a part, it was late in the evening, so to a part of the whole data set. So you select a number of images randomly, not only from the digit 2, but from all the 10 digits. And you see if these are, dimensional reduction algorithms can tell the digits apart in a way. Now, I didn't do too many experiments. Maybe one should tune the parameters better. But I ran the algorithms with k equal 9. I selected, I mean, the dataset is 60,000 of images. I selected 5,000 of digits randomly and ran the algorithm with k equal 9. Now, this is IsoMap. You can see that there are, I mean, the digits have different colors, and I've plotted some digits. You could see that you have the 0 and you have an 8 here. I don't know why you have some 8s around. You have the 0 part here. You have the 5 part here, I think. And you could tell some other pieces like 3 here. 8 is more or less here. But other stuff, I mean, they're mixed up. It's not really clear, no? Nope, what? Anyway, it does something. It does something. Maybe tuning the parameters better could help, or maybe representing it in 3 dimensions. It also could help. Because, I mean, we are handling data in, again, 28 square dimensions, so 3 dimensions is still good. This is LLE, digital classification, so you have your spike of 1s, and then everything else is, well, distributed around. The 6 are at the end, there is a group of 0s here, there are 2 here, and you cannot really see much else because it's all smashed up in here. Maybe the 3 here, but not really. I mean, even with better performing algorithms, which we'll study later, it's not always possible to completely tell handwritten digits apart, also because people really do write terribly. I mean, there are some 7 which look like some 1s, some 2 which looks like some 7, and so there are border zones between and you expect that because, I mean, it's just reasonable. But not like this. And, well, don't have high hopes on LTSA because no, it doesn't really. And if you removed here, you would see there are clusters of points here and here. So a lot of points just clustered, bundled together here. So other comments that I haven't uttered yet on this kind of stuff. The k-parameter is, the algorithms are sensitive to the k-parameter when the sampling is not dense enough. In that case, too high and too low can be both bad. And for example, for the handwritten digits, I didn't play with k, also because, I mean, the running times were comparable, more or less. They were around 30 seconds. I mean, on a not even with the compiler, so with the Jupyter Lab, which is an interpreter, 30 seconds, 20 seconds, depending on the. So nothing terrible, but you know. I mean, you could play around with that and see if they perform better. I mean, if they give better, more significant results with a higher or lower level choice of k. But I don't know. And one could also try and implement the epsilon neighborhood algorithm, which is actually not used at all with these kinds of algorithms. But it's a possibility, but just not used, because it could disconnect the, I mean, particularly if you don't know how your data was sampled, like handwritten digits, you don't have any idea on how they are sampled on your manifold. You don't even have theoretical reasons to believe that they are nicely sampled. It's very risky to use an epsilon neighborhood algorithm because it could disconnect the graph very easily. Whereas a k-nearest neighbors, I mean, it can, but it's really unlikely if you have like a uniform sample or a decent, quite dense sample. And the main problem of IsoMap is when there are holes in the data. Again, holes could be caused not only by the geometry of the data itself, but also by the unwise choice of the parameter k. LLE and LTSA are quite sensitive to noise in the data and don't handle it very well. So in particular, if you go up in dimension, the most sensible choice is probably IsoMap, at least between these three, even if it is terribly slow when you increase the dimension a lot. And that's what I was saying. Now, this is just a very, I mean, a toy comparing between these algorithms. You could try, I mean, I don't know if I will in the, I won't in the lectures. I don't know if I will in the notes or in the notebook files I will be putting on. I lost the question. Don't the 812 recommended values? But technically not. I mean, it's more of a rule of thumb. Like everyone would tell you that if you pick a number between 8 and 12, you are quite safe. Then again, sometimes they don't work. So, because, I mean, with real life data, true dimensionality is, for example, for the digit 2, the handwritten digit 2, people usually tell you that there are two main dimensions, which are the upper arc and the lower arc. Okay, that's very nice. If you plot it in 3 dimension, you don't see something which is very squished on the third one. You see something round. So the dataset also has a third dimension, which has a less likely, I mean, a less human interpretation. Which, I mean, for which it's harder to find a hidden feature causing that dimension. So from a purely theoretical viewpoint, it's very hard to distinguish between what's noise and what's a dimension. If you get after the first, like, 1, 2, 3 dimensions or something. So in a sense, well, obviously you have an upper bound for your embedding dimension. If you pick K4, you will be able to embed up to 3 dimensions with making any. I mean, if you want to make for the embedding to make any sense at all. You could try to embed in 7 dimension with k equal 4, but it will lose almost any meaning. Because of I mean, there are like covering lemmas. I mean, what's the easiest way to put it? Okay, if you cover the plane with circles, and you cover it like the best way possible so that one circle meets as few as other circles as possible, you cannot get below a given number. And this number grows with dimension. And so it estimates how many neighbors you need to, you would have in that, if something is really of that dimension. And if it's evenly sampled. So in some sense, if you want to embed in 10 dimensions, obviously you need to get to higher values of k, but if you want to plot your data or to retrieve the first 2 or 3 meaningful features, usually 8, 9, 15 at most is what people use. It's not I mean, I don't know actually if there is any proof about that, but I mean, of the fact that they are like the good choice, but it's more of a, at least to the best of my knowledge, is more of a rule of thumb that says, okay, use those if you want to plot 2D datas or at most 3D datas. So I hope it was an answer. Now, if you want to try and play with these algorithms, there are a lot of other tests you could try and make on synthetic data. So it's easy. You just take you produce your data, and it's a good exercise in geometry, and then you just see if the algorithm tells you what the trick is, what trick you used. So one thing you could try is surfaces with holes, like the Swiss roll, but you just cut a smaller. The Swiss roll is parameterized on a rectangle, so you cut a smaller rectangle inside, and you roll this thing up. You will end up with a Swiss roll with some hole going in some direction. And you try and see what happens with the algorithms. So if some algorithm detects the hole or not, or if they get crazy about it. Corners, so you could try and produce either like edges or really vertices in your data, so non-smooth data, or at least maybe not really completely non-smooth, but if you're sampling from a manifold which has a point of, we will talk about it in the next lecture, high curvature, it looks like a corner or an edge from far. High noise data, so I mean, perturbing your data with a high noise, not just like we did now. Cluster data, so almost disconnected things, or maybe things which are not disconnected but which have 2 big parts and a small connection, for example. Poorly sampled data, so not evenly sampled, and dots, okay. Other stuff you could try, curves in R3. So one-dimensional data perturbed with noise, with stuff, or just data set which have varying dimension in some sense. So which look like almost one-dimensional, and then at some point 2-dimensional, and then one-dimensional, stuff like that. And you could try, obviously, crazier things like fractals and stuff. Maybe that's a bit too much. Now, one last thing, the metric. So we had like many times the metric of the ambient space is meaningful. Like for images, the metric of the ambient space tells you how far two images are, one from the other, in a very sensitive way, because it's the sum of the squares of the differences between pixels. So now, the representations we gave in 2 dimensions didn't care about the metric. The best we could do was IsoMap, which cared about geodesics, but it's not the same. So preserving geodesic distance doesn't mean preserving the metric. It's not the same. It's the same only if your manifold was already like a copy of Rn, like flat. By the way, a cylinder is flat, but it's a product between S1 and the real line is technically flat, because just one direction of curvature is not enough. Anyway, we'll talk about it later. So yes, IsoMap renders isometrically on a particular class of Riemannian manifold, flat manifolds. A possible solution is what is called metric manifold learning, which augments the result of the algorithm. So it's an algorithm that takes your data, applies one of the other algorithms, and also computes the induced metric, the push forward of the metric. And practically by giving at each point a symmetric definite matrix which represents the scalar product at each tangent space. And so, for example, you could use that also to deform your data in your new ambient space, which is just R2, for example, to match the induced metric. So if you see that at one end of the data, the metric is more or less right, and on the other end of the data, in one direction, the metric is so the eigenvalues of the symmetric matrix are not equal, and it's diagonal, but the vertical eigenvector has an eigenvalue which is smaller. You could always, well, the right thing. I never remember which direction it goes. You could always change the. Okay, you should shorten the thing. Anyway. Or you could do other stuff, but in any case, at every point, you are told what the original metric on your manifold was. This was studied, and it's contained in a very nice Python module which is called Megaman. Yeah, I know, it's a bit funny. At least, I mean, it was maintained like some years ago. I hope it still is. Which also implements a scalable version of some nonlinear dimensionality reduction algorithms. So versions that work well when you are going up with the ambient space dimension. And well, this is everything I wanted to tell you about an LDR algorithm at this point. So I'm stopping here.